All right, this is chapter 19, problem number 14. This is a problem from your book. We're still talking about hypothesis testing for proportions. So in this problem, in the 1980s, it was believed that about 8% of children had congenital abnormalities. Some people think that number is increasing, and they believe it's because of chemicals in the environment. So we do a sample, and that sample will suggest that the number has increased. We're going to use hypothesis testing to see if that's strong evidence that it increased or if that sample was just a fluke. And then we're going to decide if we did find an increase, if we've proven that chemicals are causing abnormalities. We're going to use an alpha level of 5%. That should read 5%. So here's our solution. The first thing we do is identify our population and what we're calling success. Remember, these are groups, not numbers. So our population is children. Success is those that have congenital abnormalities. So we must write, this is an important step, let P be the proportion of the population with success. We did our sample. The number of successes in the sample was 46. The sample size was 384. So we get a sample success rate of 12%. So we used to believe that 8% of kids have abnormalities, and the sample suggests it may have gone up, possibly up even to 12%. So we write our hypotheses. The null hypothesis is that nothing happened. The rate is still 8%. P equals 8%. And then the alternative is, oh no, the rate increased. The rate of abnormalities is now bigger than 8%. Notice we have the same number here. These will always be the same number. Why did I choose greater than? Because 12 is bigger than 8. And because the problem told me to. Has the rate increased? Right there. All right, so we draw our picture. Right in the middle, we have the number we used to believe, P0, this number right here. And then we have our sample that says 12.12. We're always going to shade a tail here. So I'm going to shade above 12. Notice I shaded above, and right here I wrote above. 12 is bigger than 8. And the question says increased. Everything on the page tells me above. That's how I know this is right. All right, now we're going to do all the math on the calculator. So we're going to go stat over to tests. And we want to find a button that says one proportion z-test. That's number 5. One prop test. Hey, look, that's all the stuff I literally just wrote down. P0, the number we believed before we did the sample, that's this number right here, 0.08. I have to write it as a decimal. X was the number of successes in the sample. That was 46. N was the sample size, 384. And then here, the calculator is asking me which alternative hypothesis did I choose. What did I write here? I wrote greater than P0. So I want to choose this one, the greater than one. Not there. Hit enter. Make sure that's highlighted. Now I could hit draw here, and it will redraw this picture that I've already drawn. But I like calculate better. So just hit calculate, and we're done. So there's the z-score associated with getting this sample, 2.874. That's my sample success rate. That was the 12% right there. This is the number we care about right here. That's the p-value right there. So our p-value is 0.002. That's really the only number we care about on the screen. So we get a p-value of 0.002. Now we make a decision. If that number is less than our alpha level, right there, 5%, then we have strong evidence. If it's bigger, we don't have strong evidence. Low p-value is strong evidence against the null hypothesis. That is much less than 5%. That's less than 1%. That's 0.2%. Our p-value is less than alpha, so we reject the null and accept the alternative. So our conclusion is we can now accept this statement right here. The alternative hypothesis says more than 8% of kids have abnormalities. More than 8% of this did that. So we have strong evidence that more than 8% of children have abnormalities. That's our conclusion. Then there's this follow-up question. Did we just prove that these abnormalities are caused by chemicals? First off, that's silly. Everything is a chemical. Water is a chemical. Everything that you've ever touched in your life is a chemical. Secondly, nothing we did here had anything to do with cause and effect. All we found is that there's evidence that the rate has increased. It doesn't say why. Any question that asks you, did you prove something causes something? The answer is always no. We haven't proven anything. And no matter what the cause is, I mean, this is just a book problem. I'm not saying the rate's actually going up. But even if it had, it probably has nothing to do with chemicals. Here, we didn't do anything with chemicals. We didn't run biology tests. We ran a math test. So no, we do not have any evidence or proof that the increase is caused by chemicals. All right, that's the end of the problem. This is all just extra stuff to help us understand what we did. That p-value we got, that's the probability of getting that sample right here if the null hypothesis is true. So if the rate is still just 8%, remember samples vary. Some samples are going to be way up here. Some samples are going to be way down here. So the probability of getting a sample that looks like that any place in this region is the p-value. Is 0.002. So that p-value is the probability of getting the sample. So if the rate is still 8%, there's only a 0.2 chance that we would get a sample that looked like that. So either we did a very strange sample, that z-score we saw was almost 3 standard deviations above average, or the original assumption must have been wrong. The original assumption was the null hypothesis. That's why we rejected it. Okay, for fun, we have now found strong evidence that the rate is no longer 8%. Let's do a 95% confidence interval and try to figure out what the new rate is. The sample says it's 12%, but that's just a sample. We need to leave a little wiggle room around that. So we could do a 95% confidence interval on the calculator. We would just go stat, over to tests, and then down to A. A one prop, oh, I went way too far. It's not very responsive. One prop interval. Hey, look, the calculator kept all of our numbers. That's convenient. We're doing a 95% interval. We hit calculate. There's our interval. 0.087 to 0.152. That's the interval. So we're 95% confident that the true success rate for the whole population is between those numbers. We're 95% confident, that should say confident there. We are 95% confident that between 8.7 and 15.2% of children have abnormalities. Notice that 8% is not in that interval because we've rejected 8%. We think the rate has gone up to around 12% plus or minus, looks like about 3.2%.